We're going to start a new section today, and surprisingly, we're not going to have really tight interlocking between the previous section and the current section. We're starting a new actual topic area. But I do want to go over one thing from the homework that it's a definition for angular momentum that I didn't talk about that makes it a lot easier to do two of the problems.
Your sound quality is like really garbled. Like it's coming in like it's fluctuating a lot. I don't know how to like describe how it is, but like is there anything wrong with the system or?
There doesn't appear to be, as far as I can tell. Last time we had this, we had our IS people check, and they had similar problems going off campus and back on using the Google Hangout. So we determined it must be something with Google because it wasn't a bandwidth cap for us. Yeah, it's coming through garbled on the other computer that's connected. So, and yeah, they checked the equipment. It wasn't the equipment. So we'll have to do the best we can. Sorry about that. Okay, the equation that we know right now for angular momentum is angular momentum vector is equal to I times omega vector. And that's a true and correct equation. I don't want people to think, and now I'm giving you, that was wrong. That's correct. But there's another equation to it that actually relates highly with the torque equation. Remember, we know that torque is equal to radius crossed with the force. So if I have a force acting on an object, the torque is the radius, the lever arm, which is the vector that points from where the force acts to or actually from the place where some of the torques to where the force acts. And then cross to the force, which means we're only multiplying the perpendicular parts. So that has a magnitude. So I'll put magnitude sign for the torque is equal to the radius times the force times the sine of the angle between those two vectors. And of course, we've learned that there is a simple relationship between the net torque and the angular momentum. And that relationship there is what leads you back to the new equation for angular momentum. Radius crossed with linear momentum. That new definition you can see works through if you take the definition of torque and then using Newton's second law with the linear with the definition of force and changing linear momentum over change in time. So this equation, they're equivalent, but for problems like this one, it's going to be easier to use angular momentum is radius crossed to the momentum. Now, what does it mean again when I do a cross product? I'm multiplying the perpendicular parts. So if I have the starting, I don't know how many people are Monty Python fans, but this problem is an homage to the Search for the Holy Grail. This is a laden swallow, by the way, not an unladen swallow, so it's not exactly what the challenge question was. But you have this swallow that's flying, and if you look at its angular momentum before it drops it, you're going to say that it has, the radius is constantly changing, right? The radius is going to be this vector here, constantly changing. But I'm multiplying the perpendicular part between the momentum and the radius. So finding the perpendicular part is kind of easy because the perpendicular part is going to be the closest approach, which is when it's directly overhead. And the problem gives you what that perpendicular radius is. So the angular momentum that this coconut, everything we're doing has to do with the coconut, not with the swallow. The angular momentum that coconut has initially is just going to be that height. And notice it says magnitude, so I dropped off the vector sign. That height multiplied by the momentum, which is the mass times the speed, because those are perpendicular. The radius is up, the momentum is horizontal. If you wanted a direction for this, you'd use your right hand rule, vertical for the R, and then to your right for the momentum, and my thumb points into the screen. So the direction for this angular momentum is into the screen. And so that's easy enough to calculate. In fact, it's very easy if you know this definition to calculate. Now, when you get further, and I'm going to jump down to, I think it's D. Yes, D. Calculate the magnitude of the angular momentum 1 second after it drops the coconut. Angular momentum is not conserved in this problem. The problem before this, you'll also benefit by using the angular momentum as R cross P. But in that problem, the angular momentum was conserved. Here, the angular momentum is not conserved. What's the difference? What makes the difference in when angular momentum is conserved versus not conserved? I'll step back one step to what we had in the test. What's the difference in linear momentum being conserved versus not conserved?
Net force is 0.
If the net force was 0 in the direction we're interested in, then linear momentum was conserved. If the net force was not 0, then linear momentum was not conserved. So if we're looking at rotation, we just have the equivalent rule for rotation. If the net torque is 0 about the axis we're interested in, then angular momentum will be conserved. Well, in this case, there is a force of gravity acting downward on that coconut. And so that's going to create a torque. I can take this R vector and this force vector and calculate the torque, right? It's not 0. So angular momentum is not conserved in this problem. So don't try to say, oh, this is just going to be the same as I had for A. It's not. It's definitely different. So then the question is, how do you do it? Well, we can break this into two components. We can calculate at this location, it has a Vx, that's an X, and a Vy, those two components. And of course, the radius can be broken up into its components. So I'll have an Rx and an Ry. And if I'm calculating the torque, I'm taking the perpendicular components and multiply them together. So I have two sets of perpendicular components here. I have the radius in the x direction and the velocity in the y direction. I also have the radius in the y direction and the velocity in the x direction. So I just calculate both of those separately. So now we have to make sure we have our directions right. If it was flying the other direction, well, yeah. If it dropped it over to your left, we would have a different result because the positions matter. So just think about the two put together. Here's my Ry and Vx. Using the right-hand rule, you always put your index finger in the direction of the first vector, middle finger in the direction of the second vector. So since it's R cross P here, that's the same as mass times R cross V. You're a bad person.
Why am I a bad person?
I don't know if you did it intentionally, but it looked like you were.
This.
Oh, okay. That was index finger. I thought she was flipping me off. You're a good person. Okay. And of course, I didn't think she was intentionally. It just looked like it. Going back to this and staying very appropriate. Index finger needs to point this direction, just like Rachel's finger was doing. Then the middle finger points this direction, and my thumb points into the screen. So the direction for the angular momentum that is involved with Ry and Vx is into the screen. Now, if I look at the Rx is like this, and Vy is like that, using the same right-hand rule, index finger pointing to your right, middle finger pointing down, that's also into the screen. So you're going to get the same direction for both of them. And so you'll just calculate the magnitude for the angular momentum is Rx/Vy plus Ry/Vx. And for people who've taken some higher math classes, you can actually do this. The determinant method, you would say angular momentum vector is equal to x hat, y hat, z hat, Rx, Ry, Rz. I better put P here. Px, Py, Pz. You do that determinant and note that Rx is equal to 0, Px is equal to 0. That makes the x and y components both 0 in this calculation, and you only get a z component. And it turns out that you have equals the z direction times Rx Py minus Ry Px is what that equation gives you, but your Py was a negative number because it's going down and y was up. And so it comes out to be magnitude-wise if you're using the magnitudes of the velocities. So don't use this equation and put minus for Vy. I did that using the magnitude of Vy. And I leave part E to you. Part E is just calculate again, just before it hits the ground. Every now and then somebody thinks, hey, I'm smart. After it hits the ground, it's going to stop, and they just say 0. No, but it's asking for the instant just before it hits the ground, so before it stops. And so you just have to find what the R's and Y's are just before it hits the ground and do it again. So I want to make sure that we covered that because I didn't talk about this equation. The problem, it could be done with what I gave you before, but a lot more work. It's a lot less work using this R cross P for angular momentum. Okay, question.
For calculating right before it hits the ground,
Yes.
when you said find the y's,
Well, you need to find the values of its position components, its x and y components for position, and its velocity components, the velocity in the x direction, velocity in the y direction just before it hits the ground. And so you need to find both those. And so this is where you're going to use what we learned a long time ago in kinematics about, independence of motion, the vertical direction. It starts at a speed of 0 and drops under the influence of gravity. Horizontal direction, it has no acceleration, so it's just a constant speed for the horizontal. Question, Brady.
Just to make it more, so I mean that's Rx Vy plus Ry.
Is that better? Is that what you talked about? Yes, I forgot it. Oddly enough, when I was working out my solution, I forgot it there too, and it became abundantly clear to me these numbers don't look right. All right, any other questions about this? Because, practicing and being successful in the homework is so much more valuable than practicing and banging your head against the wall. And if you're feeling that head against the wall banging, send me an email. Caitlin, I got to yours, but it wasn't until this morning because, Oh, was it Aaron? Okay, Aaron. Okay. But it wasn't until this morning because I went to bed. Okay, new material. We're going to start studying now about fluids. Fluids are things that flow. So anything that flows fits into that category. Does water flow?
Yes.
Obvious. Does air flow? Yes. So those are obviously fluids. So we're going to learn about fluids and how to deal with them, but we start with just a very brief introduction to the states of matter so we can identify what we're dealing with. So there are 3 common states of matter that we talk about. And I know there's some people saying, no, there's a 4th common state. I do have that on the next slide. These 3 common states are common states for, let's say, uncharged matter. So we start with a solid. And this is very specifically a crystalline solid. If it's a solid, that means it has a fixed shape and a fixed volume. Why does it have a fixed shape and a fixed volume? Because the atoms or molecules are bound into positions where they can't break free of each other. And as I mentioned, yesterday for the Physics 251 students, we treat the bonds between atoms and molecules like they're springs. So for physics, we just say it's like a spring, force of minus kx, where x is the amount you displaced it from its equilibrium position. In a crystalline solid, you have very reproducible long-range order. All of the atoms are lined up in a certain way, and they can't move. They can do little vibrations. And temperature is a measurement that tells us about how much energy they have in those vibrations. So if it's low temperature, they're not vibrating much at all. In fact, absolute zero is an idea because there has to be a minimum motion. And the minimum motion possible is what we call absolute zero. If you're taking like a high school level physics class, your teacher usually says and probably usually believes that absolute zero means the cessation of all motion, that everything stops moving. Well, quantum physics says that's not possible. That at absolute zero, there is a certain amount of motion still occurring. But, for a very beginning understanding, we treat absolute zero as the cessation of motion. So minimum possible motion. You increase the temperature, they vibrate more and more and more. Well, just like having a mass on a spring, if you make it vibrate with a big enough amplitude, you can break that spring, right? And that's what happens when you melt a solid. When you melt a solid, you get those atoms vibrating so much that they have enough energy that an atom breaks free. And so that brings us to the liquid stage. So the next stage here is liquid. In the liquid state, I shouldn't say stage, I should say state. In the liquid state, your atoms are now free to move about the country, so to speak, but they can't leave each other. There's still a force that holds the atoms all together, so they can't actually escape, but they can move past each other. They're not in a fixed position. And so the liquid, notice for the solid, you had a fixed shape and a fixed volume. For the liquid, because they're free to move around each other, the shape can change. You only have a fixed volume because they're all stuck together. And now, once again, if we want to be purists, we do know that a solid can be compressed by a very small amount. A liquid can be compressed by a very small amount. We tend to call them incompressible, but the fact is they can very slightly be compressed. So this fixed volume is within the understanding that, okay, you can, if you apply really large forces or stresses, get small changes in volume. Well, of course, now we have the liquid. Molecules are moving past each other. When a molecule gets to the surface of the liquid, it can't escape usually because it doesn't have enough kinetic energy to overcome the potential energy of being connected to other molecules. But as you go faster and faster, i.e. as the temperature goes higher and higher, then the molecules coming to the surface have more kinetic energy until some of them have enough kinetic energy to break free. And so when molecules break free of the liquid, then they really are free. They are free indeed. And so that is the gas, and they're just free. So in this room, we have air that's a gas, and the molecules in the air are just flying about. And they'll fly until they hit something, which is not a very large distance at all for this room. If you were to go out into the, quote, vacuum of space, the molecules might travel a kilometer before they hit something. And they just fly freely until they hit something, and then they bounce off of it. And so that's what's going on with a gas, and because it's free, it will just fill its container. So if I had just one molecule in this room, I would say that molecule fills the room. Its volume isn't equal to the room, that molecules isn't. But the gas is because it moves around and will cover the entire volume of the room over time. Now, in this room, we all know that we have many moles of gas, right? Somewhere in the ballpark of 10 to the 25th molecules of gas in this room. They're very thick and they really do physically fill the room. So those are the three common states of matter. But let's look at some uncommon states. First, the plasma. Many people like to list plasma as a fourth common state of matter because things like the sun, as the song goes, the sun is a miasma of incandescent plasma. That was They Might Be Giants' rebuttal to their cover of the song, The Sun is a Mass of Incandescent Gas, in case people are fans of They Might Be Giants or educational songs in general. So the sun is an ionized gas. It's still a gas, but because it's ionized, which means that you have charged particles in the sun, the temperatures are far too high for electrons to actually be bound to protons. So you have an electron gas and a proton gas coexisting, and those are both plasmas. Notice I said electron gas, proton gas, both plasmas. Plasma is a term for a special kind of gas. And we see those commonly. So this picture shows two common plasmas. One, a neon lamp, or the same thing that's going on with the fluorescent lamps above us. They have plasmas inside. In the fluorescent, you have a plasma with it's mercury, I believe, and then you have phosphorus coating the inside of the tube to absorb the ultraviolet light from mercury, because that's not good for the old eyes, and then give visible light. And then, of course, these little balls are really cool. You're making plasmas in there, and you can put your hand on there, which essentially puts a ground on the outside of the glass and makes the charged particles it's very cool. So that is, some people consider a fourth common state. General physics textbooks generally don't consider it a fourth common state, and then some physicists get irate. Glass. Glass is an amorphous solid. So it's a solid, right? Everybody knows glass is solid. You got a window back there, you can bang on it. It's solid. But it's not a crystalline solid. And remember on two slides earlier, but the preceding one lecture-wise, I said I was specifically talking about a crystalline solid. A crystalline solid, the atoms have a very long-range order, right? Atom here, go another distance, another same atom. Go that same distance, same direction, same atom. That's how crystals are. Whereas a glass or an amorphous solid has the molecules kind of haphazardly placed. You still have bonds holding all the molecules and atoms together, but it's not long-range order. That occurs because of the way you freeze it. On the wrong one, that's going to disappear. Because of the way you freeze it. So obsidian, when I was a kid, we'd go camping and I'd always be scouring the ground to find those obsidian arrowheads, because in California, they're pretty much everywhere. And that obsidian is a glass. A lot of people don't realize obsidian's a glass, but it is. What makes it a glass? You had magma, molten rock, that cooled extremely quickly. Because it cooled so quickly, there wasn't time for long-range order to be set up. And so you have no long-range order, no crystalline structure, and thus when you fracture it, it just fractures randomly because you don't have that long-range structure. And so that makes it glassy and allows you to make very sharp edges, hence the Indian arrowheads. So obsidian, this is what obsidian looks like here. Now I do want to not have the one that's permanent. Well, nice job. That's what obsidian looks like. It's pretty. The glass that we have in our windows, it's silica-based, just like obsidian is. That is, you have silicon dioxide is the fundamental build unit for glass. And they put lots of different things in there. You might have soda lime glass or something. But basically, they heat up and melt this silica with whatever impurities, if you will, whatever other atoms. Okay, so that wasn't a microphone. That was me tongue-tied. They want to give it the properties they need for the glass. And then they need to freeze it rapidly so that it doesn't form long-range structure. If it forms longer-range structure in rock, most ocean floor beds are basalt. Basalt and obsidian are the same thing chemically. But the difference is the basalt took a little longer to freeze, and so it has some very small crystals, some very short range order. If it cools really slowly, the same exact chemical composition, if it cools really slowly, the crystals grow larger, and then we call the rock granite. So granite, basalt, obsidian, they're all the same rock fundamentally. It's just how big the crystals are. So the obsidian is an amorphous solid, a glass, and then you have bigger crystals going from granite and then basalt and then to granite. Liquid crystals, I just included those because lots of us have things like a liquid crystal display in a calculator or on a cell phone. And the reason we have those is because the liquid crystals they use, it's a liquid, it flows, but it has a long-range order. And because it has that long-range order, it has a crystalline nature, hence liquid crystal. The liquid crystals they use here, you can change the polarization of light by putting a voltage across it. So they can use it as a light switch by putting different voltages. And so that's why you turn on and off the display by just putting different voltages across that liquid crystal. The last one I have is a colloid. A colloid is a suspension of one type of molecule with another fluid that doesn't mix with it. And a common example is milk. So this picture, the last picture here, that's looking at milk under a microscope slide. The little circles are little butterfat globules. And then you have a water-based solution that is dissolved in. And the color of milk, that white color, is because of scattering off of those little butterfat globules. It's the same reason that clouds look white. So those are 4 additional states of matter. Mahala.
So would basalt and granite then be crystalline solids and not amorphous?
Basalt and granite are going to be, people probably aren't going to put them in any of those categories because you have some crystalline nature, but then you also clearly have that it's broken up. And so in the only difference is how big the crystals are. In basalt, you look at it under a microscope and you can see the crystals. Granite, you can see them with your naked eye because they're bigger. Okay, so our first clicker question. Fluids are materials that flow. That is, they do not have a fixed shape. Which states of matter listed below fit the definition? So put in all of the ones that are correct and hit enter. Obviously, there's more than one correct answer here. And I am going to have a large number of people answer because I'm going to have the first card will explain what their answer was on colloid and work our way through that way. Okay, Branislav has his answer in, just making sure. Okay, give it another 5 seconds here. And our breakdown was 20, perfect. 22 said a colloid, 41 said a gas, 7 said a glass, 49 said a liquid, 29 said a liquid crystal, 34 said a plasma, and 1 said a solid. So the first person who gets to explain, and so this would be explain if you said yes or no for colloid and why, is Joel Lozano.
Sorry, what?
Okay, for the colloid, did you say that was a fluid or not a fluid, and
I
why?
didn't know what that was. I just had to look it up. But I didn't put that one. I put the next one. Yes.
Okay, said he had to look it up. He wasn't sure. Okay, the colloid was the suspension of soluble material in a liquid. So example, remember milk was an example of a colloid. So all you really have to do to answer this is say, well, do I consider milk a fluid? If it's a fluid, it flows, so I can pour it. Can I pour milk? Yes. So that was a correct answer because you can pour it. Next person, Kimberly Alba. Tell us about gas. What did you say?
I said yes.
Okay. And why?
It doesn't have a fixed shape.
All right, that's perfect. A gas does not have a fixed shape. That means that it can flow. And so it is also a fluid. Next person is Caitlin MacArthur on glass.
I said it wasn't.
And why not?
It has a fixed shape.
Okay, she said it wasn't because it has a fixed shape. 7 people disagreed with her. There is a very common, I'll say conception, I won't say misconception, that glass is a fluid. Because given a lot of time, glass will flow. How many people have heard that glass flows? Okay, most of us have. And Caitlin, who just gave her answer that has a fixed shape, raised her hand. She's heard that. Well, we hear it so often that sometimes physicists get a little frustrated. So a guy actually wrote an article where he talked about this and did some calculations. You probably have heard things like if you go and you look at the windows in an old house, you can see they're kind of wavy because the glass has flowed. Au contraire. His calculations showed quite clearly you would have lost all of the lead they used to hold that window pane in long before you could notice any kind of flowing in the glass. Everything flows to some extent. If I take this mass and hang it over the edge, and if I leave it there for 1,000,000 years, it will have descended on the part that's not supported by the table. Everything flows to some extent. But glass flows really slowly, really slowly. Things that flow faster, ice, for instance. So to think of glass as a fluid there is a technical way to think about it that way, but it's really not the correct way to think about it. It's a solid. So it shouldn't be that, hey, look, surprise, it looks like a solid, but it's a fluid. Lead is much more of a fluid than the glass is. So your answer is the conventionally correct answer. And if you were to have answered a fluid, then you'd have to answer, well, and everything is a fluid, if you're going to use that as your divine point. Okay, so the next one on our line to talk about a liquid. Mahala.
So it closed as soon as I clicked it, but liquid was on my list, and it's because it's free flowing, like the definition.
Okay, just because it's free flowing. And you are correct, Mahala. And the gas also, it's free flowing. Just make sure we got that down there. Okay, so the next person, the liquid crystal, something that's new. Rachel Gregerson.
I tried to put it in before, but it was closed again. But the definition is flows like a liquid, but as a long range order like a crystal.
Mm-hmm.
So it does flow, but has the form of a crystal.
Yeah, and so it's interesting in that regard because crystals we tend to think as solids, right? Fixed positions, but it can flow, and so I'm sorry, I obliterated the 29, but you're correct. It flows. Okay, next to last, plasma. Plasma goes to Jasleen Escudero Rios.
It does flow.
Okay, and why?
Because it's in your blood.
I didn't hear the last word because it's
In your blood.
It's in your
It's
blood.
their blood.
okay, this is our blood. That actually is a different definition of plasma. You are correct that our blood has plasma, but that's a different definition for plasma. Can't fault the person for using a correct definition here, now can I? Okay, so the plasma we're talking about in well, today, is a plasma that is a gas of charged particles. Because it's a gas, it does flow. And finally, Andrew Nelson is going to talk about solids that one person said yes for. So, Andrew? Not that, okay. Then he won't talk about it. Instead, Kelly Michelou, like LeBeau, right? For the solid, yeah. Okay, she said not a liquid because it doesn't flow. Even though the molecules can move small amounts, they can't move past each other, it can't flow. Okay, so got all of these clicker questions out of the way. We're going to get through everybody by the end of the semester if I do this many per day. Density. We've had density since like chapter 1 of the textbook as an example of something with units. Density, we use the symbol rho for. That's a lowercase r in Greek. And it's defined as the mass divided by the volume. Different things have different densities, and this density becomes a very important idea. When I was in graduate school, I was studying sapphire. And we have sapphire crystals that are ground into, we were using 1/2 inch thick, inch in diameter cylinders. We had sapphire crystals and we had quartz crystals. And looking at them, you can't tell the difference. They're both perfectly clear. And so we have to do other tests. And one of the tests I did was just to measure the density. Measure the mass, measure the volume. The density of sapphire, that's Al2O3, is very different than the density of quartz. So that's one way to tell the difference. Now, we did other things as well. I measured the speed of sound in them because sapphire has, I think it was a higher speed of sound than quartz. And then I used a Laowa camera to actually do crystallography and make sure I had the right orientation for my samples. But density was the first and best test. So it's important. This picture is, in theory, comparing a ton of bricks to a ton of hay. A ton of bricks and a ton of hay, if they fall on you, it's still going to hurt either way. It's the same amount of weight, but the ton of hay is a much bigger volume. It's much more spread out. And so if I were to take a little chip of a brick and a little chip of the hay, same volumes, the brick would be much more massive for the same volume. And so it's something that we use to differentiate materials. And now a question that Mahala asked when we talked about stress, she asked, well, what's the difference in stress and pressure? Because most people know pressure is force divided by area. And this picture helps to confuse the point because it's supposed to be talking about pressure and yet it, is clearly showing a stress. If I take my finger and I press on something, that's a compressive stress. It's a force going into the surface. And of course, my finger pressing on me, no pain at all. If we take a needle and we press on us, you know what? That really doesn't have much pain either. It makes me, I don't scream like a baby anymore. But even when I was in college, having my blood drawn, I would get so uptight, blood vessels would collapse. It was all bad. Because I really don't like the idea of something puncturing the skin. But you put a force with the needle and it just goes right in. Because the actual force per unit area is a small area, so a big ratio. And so you would have, for the same force of a finger versus a needle, finger's never going to penetrate, the needle does, because the force per area is much, much bigger than the needle because of that small area. So we're going to start dealing with pressure here quite regularly. And pressure is different from stress because it's in all directions. So this picture shows the inside of a, let's say, an automobile tire. And so you have air pressure inside. The air has pressure caused by molecules bouncing off of things. And that pressure puts a force on any surface that the air touches. But the force from pressure is always into the surface. So in this picture, these arrows are showing the direction of the force for each surface. And so you notice those arrows are always into the surface. And if you look here at the valve stem, you see the force is going into everything there. You can very easily see how the whole valve stem thing works. You push down on that center thing, and it pushes this whole thing down, and air can slip back, go out, or go in. If you release it, they have a spring to help, but even if you didn't have a spring, the air pressure inside will put a force over that surface that pushes it back closed so air doesn't come out. So it's a pretty simple device. Now, one thing to point out with this, we use tires on our automobiles. What is holding up the car? Now, this is a real simple question. What is holding up the car itself? Not what's holding up the axle. What's holding up the car? Okay, that's a little more complicated than I was actually looking. I was just looking for, we have, the tires are pushing down the ground, Newton's third law is pushing back up on the tires. So the ground pushing up on the tires is what's holding up the car, is what I was looking for. But then we look at this, and if you look at this, you know that the tire sidewalls aren't, they're not rigid. And so you're like, well, how is that going to hold, or I am like, you might not be, how is that going to hold up the car when I know that the sidewalls aren't rigid? And the answer is that I have a certain amount of area down here in the bottom of contact between the tire and the road. And so the road is putting an upward force on there, and the air inside has to be putting a downward force on that piece of tire that's going to balance the upward force of the road. Now, since pressure is force divided by area, then that means that the force that the air provides is equal to the pressure multiplied by the area of contact. So if a tire needs to support more force, that area of contact is going to have to get bigger, or of course, you have to have a higher pressure. And so if you weigh down a car, the tires will flatten down a little bit because you need a bigger area to get the same, the upward force, downward force in this case, on the rubber necessary to counter the upward force of the ground. So you can take for each tire the pressure inside of the tire multiplied by the contact area between each tire and the road, add those all together, and that's going to give you the weight of the car. Question?
So if the tire is being pressed down to the ground, that's effectively lessening the volume inside the tire just a little bit. So if you have a heavier vehicle, would the pressure be different?
The pressure would be very, very slightly, but yes, different. Buoyancy. Now we're going to study buoyancy more carefully, probably not Friday, but Monday. Buoyancy is the result of us being surrounded by a fluid. Let's take right now. I'm standing in the air. There is an air pressure pushing on me. In 2 slides or so, we'll talk about it. But the air pressure, by the definition, is putting forces to go into my body everywhere it touches me. So the top of my head, the force is downward due to air pressure. What about the side of my cheek here? It's going in. Here, it's going in the other direction. Well, these forces are going to cancel each other out, so the net force side to side of my head is 0. But air pressure is actually getting bigger as I go down. So the force pushing upward on the bottom of my shoes are not sealed to the floor. There's air that flows between them and the floor, and that air is pushing up on me. With the slightly higher pressure, slightly higher force per area, then it's pushing down the top of my head. And so since I have slightly higher pressure pushing up on my feet and lower pressure pushing down on my head, the net result is I have a net upward force because of the higher pressure on my feet. Do I notice it? No, I don't go, I can fly, because it's a very small difference in pressure. But if you're in water, water is about 800 times more dense than air. And because it's about 800 times more dense than air, the pressure increases much more quickly in water. And so if you're swimming, the pressure underneath is bigger, hence the force. All of these arrows are supposed to be force arrows going directly into each part of the body. The forces on the lower parts of the body is bigger, pushing up, than the forces downward on the higher parts of the body. Hence, you have a net upward force when you're in the water, which we call a buoyancy. And so that's why I can now float. Ever since I got heavy, I could float. Back when I was light, I sank. Why? What's the difference? Well, everybody knows. Muscle, high density. Fat, low density. And so because I've built more fat than muscle here, I now sink because of my greater density. Or lower density, I float because of, way to do that. So let's talk about this pressure changing with depth. The pressure can be calculated here fairly simply. Here I have a picture with just a cylinder of water. And so the water has density of water is equal to 1 gram per centimeter cubed. That's the density of pure water at, I think it's 4 degrees Celsius. I might have temperature wrong. It changes with temperature, but that's what we use for our average value. I have this container that has some unspecified surface area A and some height H. So I have the weight of all of that water has to be supported by the bottom of the container. So I can calculate how much force that water puts on the container by saying the force of the water is equal to the mass of the water times G, right? The weight of the water. And so the mass is going to be the volume times the density, since density is defined as mass over volume, then just solve that for mass. Volume times density times G. But then for this cylinder, so now I'm going specific. For this cylinder, what's the equation for the volume of a cylinder? It's okay, pi r squared, the area of a circle, so I just put A here because that's what it gave us, but the area of the circle multiplied by the height. So going one step further, the area of my circle multiplied by the height of the water times the density times G. That's the force the water is putting on the bottom surface. Now, if I want to know the pressure of the water at the bottom, I know the pressure has to be the force that the water is putting on the surface divided by the area of the surface. Notice my areas now cancel, which is why it used area rather than pi r squared. And so we get the pressure at the bottom is density times G times the depth of the water. So if you go down lower, the pressure is bigger because the weight of the water increases linear with depth. What if this cylinder had a chamber that came out to the side? Would the pressure over here be the same or different than the pressure here? Okay, I have one person that says the same. Proudly and loudly. Why do you say that?
Because how do I say this? The density would be the same at those points. I don't know if that makes sense.
The density is the same, but it actually comes down to the technical term. It's the hydrostatic. That's a D. Obviously, my mouth said S for static, and my hand followed suit. The hydrostatic pressure. If I have a fluid, the hydro, and it's static, stationary, that means that it must be in equilibrium, so the net force on anything is zero. So if I were to consider, let's say, a little piece of water right here, the force pushing it this direction has to be the same as the force pushing it this direction, or it's not in equilibrium. And so if it's a little cube, that's going to have to be the pressure on one side is equal to the pressure on the other. Now, if we did in the vertical direction, I would have the force of pressure down and the force of gravity on that cube down, and the force of pressure down below. That means the pressure below has to be higher to take account of the additional force of gravity. But side to side, it has to be the same. So the pressure has to stay consistent if you stay at the same elevation and move horizontally. But just a minute ago, I calculated the pressure because I said it's due to the weight of the water above. Now we're off to side and it doesn't have that weight of the water above. But because of that pressure, you actually have additional downward force that's caused by the chamber to make up for the missing water. I obviously have to end with this slide. If we look here, a dam, notice the dam is much thicker at the bottom than on top. The reason for that is simple. The pressure is much bigger down lower. So the force that the water puts on the bottom of the dam is much bigger than the force it puts at the top of the dam because of that relationship that force is pressure times area, and the pressure increases with depth. So the construction of the dams has a very simple reason. There's also torque reason, but that's where we'll stop today. All right. Have a great day. See you on Friday.
That just is,